Looks like I'm all set.
Yep.
Yeah, thanks for the opportunity to speak today. A little bit different talk than you've seen in the first two, but as Will mentioned, Tomorrow I/O was one of those successful transitions of a technology, the TROPICS missions, into the commercial space. And so hopefully they also take a little bit of pride in the research to operations stuff that we'll show, or at least they don't take any offense to anything we've done. So the thing that I should mention as we talk about R2O and the impact of tomorrow's microwave sounders on our products is that we have to think about the Tomorrow as a company as well and what some of our goals are. So overall, we of course have customers and we need to equip them with actionable weather insights. That's sort of the business model behind this. And that's done through a weather software as a service application and a platform. So that's meant to be demonstrated in that box on the right. Of course, under the hood, everything that we deliver to our customers needs to be coming from both publicly available weather information sources. And if we want to really add value, it needs to be coming from AI and physics-based weather models that we've developed specific to some of our customer use cases. And so there needs to be this healthy R2O transition there. We also know that a lot of the limitations that we have in the skill of our weather models really comes from the data. The observations that feed these, that initialize, whether it's a short-range weather forecast system or a global precipitation retrieval like you'll see today, the limitations generally come from the observations available. So it's really unique to work at Tomorrow I/O, which has sort of these three business sectors and allows us on the weather modeling side to really both have access to the customer end cases, know what we're building and why, and also have tools upstream of us, really good technological advances that we can do something unique and novel with as we work towards this, again, pipeline of research to operations. And I'll note that the version of the satellite retrieval that I'm going to share with you guys today, that's sort of the third iteration of this, the third time we've gone to customers with a new model. And in this case, we're also going to describe a little bit about after a year of operations, what we've sort of recognized as limitations in that and where we go from there with the next version 4, now that we do have a full year of the Tomorrow microwave sounders on orbit. So just to briefly, I'll note that Joe Munchak, who many of you probably know, is going to have another talk later this week on Wednesday, where he'll discuss the current status and on-orbit performance of sort of the level 1 algorithms for TMS. Just very briefly, this is, again, is similar to the TROPICS mission, 12-channel, 91 to 204 gigahertz, and for retrievals of profiles of temperature and humidity. And where we're really going to be discussing today is the sensitivity to hydrometeors as well, which gives us some ability to do something unique and novel in terms of a global precipitation retrieval. Note one additional thing that we have about a 15 to 30 kilometer resolution depending on channels. And also in the nature of R2O, I'll note that individual TMS have been integrated in about a span of 1 to 2 months after launch. So the initial ones were launched back in October. The algorithm that we originally trained that on was trained on TROPICS, sort of this deep learning precipitation retrieval network. And so we did a transfer learning approach with the first set of these TMS sounders in our precipitation pipeline. And with each new launch happening, we go through calibration and checkout and then can start to work with that sounder data directly into our systems. A lot of the motivation, again, is around that sensitivity of the sounders to hydrometeors. So many folks in this room, I acknowledge, know this much better than me. But if our motivation is to have a globally available radar-like precipitation layer, we, of course, can look at what a radar would demonstrate in a storm system, in this case, over the southeast United States. And so you see real strong precipitation structures, and that's sort of the best available information we have on the spatial and temporal evolution of precipitation. By contrast, outside of radar coverage, it's mostly the geostationary satellites that give us that consistent global picture. And unfortunately, with those, they're very sensitive to the cloud tops, the visible and infrared information kind of saturates and you don't have much information about precipitation processes within that. So we're looking to the microwave sounders to give us some additional information to really build neural networks that can kind of understand the value of each different piece of information in the overall puzzle to create something much larger than the sum of its parts. I should also note that, again, with customers globally, we have to do this in full global coverage. And what I'm showing here is sort of the broad distribution of different radar networks that we have available to serve as precipitation targets in different sort of precipitation regimes around the globe. Can, of course, also use things like the DPR as a target. And then for inputs to a precipitation model, we have each of the individual geosats available. This is an older image from the time that we released this. So Meteosat 10 has been replaced with MTG for that domain, of course. And then I've also got a band showing TROPICS because we did leverage the TROPICS instruments in that retrieval algorithm for training. And so anytime we have that information available, we need the network to be able to leverage it, knowing that it's providing potentially additional information beyond just what a geostat can see. The end goal to be able to generate a precipitation image that looks something like this, where on the left we have Helene making landfall back in 2024, and you can see it coming into the radar network coverage. Whereas on the right, we have sort of a more global picture that's leveraging the geosats and I'll also demonstrate briefly the microwave sounders here in a second. But that's sort of the backbone and motivation behind creating this global precipitation product at, sort of kilometer scale resolution that's refreshing every 10 to 15 minutes based on the geosats, or if you actually want to anchor it as an event-driven workflow on any microwave sounder information that you have coming in as well. Just in terms of the verification, since this is an R2O thing, I'll note that for the manuscript and papers and all that, we do a full testing data set. And we see just on the left, this is just a demonstration of how we compare in one inference case against station observation network that's available sub-hourly for us. And we see a front coming across and are able to evaluate precipitation rates for each of those. And we do that in bulk on the right to get these statistics. And we can see Heidke skill scores, if I just briefly highlight maybe one or two columns here, with a threshold of a quarter inch per hour, or 0.25 millimeters per hour, which is just sort of presence absence, or 6 millimeters per hour, which is sort of a fairly moderate to intense precip rate. You can see Heidke skill scores from this version 3 of our algorithm. At light rain rates are significantly closing the gap relative to what you might have seen with IMERG final product or our previous version. And then relative to MRMS, when we're looking at some of those more intense precipitation rates against stations, we're actually scoring pretty well. Obviously, there's some challenge in verifying against stations there that you see both sets of metrics being quite low. But that's the kind of thing that we have to do to evaluate our systems in this sort of R2O space. It's not just a research thing. This is actually being used to drive decisions all over the world. And so we also need to evaluate our precipitation retrievals and their utilization in nowcasts as well at station networks where we have them available. And so this image here is now going to be 4 separate timestamps from the real-time retrieval. We wind up having about a latency of 10 to 15 minutes with any precipitation retrieval that's actively happening. The sounders, of course, there's sort of this window where you're trying to assimilate information from. So those can be quite older. But when I have T+0, that's roughly a 15-minute true latency in operations. And these would be our nowcasting systems. And a blue dot means that this nowcast from the satellites is actually exceeding whatever the baseline forecast is. So most of the world, that'd be against ECMWF, for example. Not hard to beat a physical model in that case. But in some of these other ones in the US, maybe that's against HER, which is assimilating radar systems. And so we kind of take that approach to really understand if we're providing something of value to our customer base. And more importantly, too, since this is an R2O thing, it's also worth noting that we do the R2O phase, successful transition, can demonstrate value, gain some funding from that. But it also has to come back to the research phase after we see something like this. There's plenty of red on this map that motivates us. What are we going to do in version 4, right? Another thing with version 3 was we were able to do data denial experiments where we could understand the impact of the microwave sounders. And so this was executed on the first 2 months. You can see, for example, on the left, just an image. This was of Milton in this case. And it's demonstrating the skill scores when we have a sounder come across. In that bottom left one, we can see the skill of our retrieval systems jump up relative to the radar as it starts to use that information. We see that that functions in bulk to some extent, but we know that now we have a full year of TMS data on orbit. We've got 11 sounders up. We've collected thousands and thousands of samples that can be used to come back and retrain these algorithms now. So we've learned a lot of lessons from this first R2O phase. And those are going to drive us to come back and look at what are the things that we can do to improve the skill scores. But also, it's an operational product. How can we improve things like the latency and the stability of it? When a geosat drops out, we want to ensure complete coverage. When we have a channel go bad on one of the TMS, we want to ensure that we can be flexible and pull the plug on something that's not working. And so there's a lot of additional pieces to consider beyond just the academic skill of a model like that, and also just how it can actually function for us and make our lives easier. It truly is operational for us. We're on call, we have data dog alerts and pager duty. When something doesn't work, it's going to wake us up. So it really behooves us to put as much effort into the systems as possible. And I'm getting close to the end here. I really hesitate to show ugly slides in a talk like this, but I think because it's R2O and now we're going back to R, it's warranted. And I want to pitch this in kind of the way of like, let's just look at what kind of information we've actually gotten from a given day of TMS. And so this is in June. I think we had about 7 satellites functional at this time. And this is just a 24-hour period. This is colored by the age in minutes of the TMS data coming across the scene. And you can see that it's sort of these, if we're just looking at the central southwest US, you've got really sparse and variable coverage over the course of the day. And we're really motivated to understand, can we build a system that can handle this really well? Not just anchor itself on the geosats, right? Geosats have been used for a long time. They've been skillful, but can we really do something that is native to this type of data and therefore has a much higher ceiling? And so I'll bring in now the brightness temperature. I've got my red light flashing, so just bear with me for a second. And I'll show just a 10-minute retrieval from just Tomorrow microwave sounders. And so, of course, the precipitation data is not going to look great in this case, but this really is just driven by that TMS data. So whether it's a 30-minute latency or a 6-hour latency between individual revisits, it can create a skillful precipitation retrieval just from that. And that should be the starting point for us to go forward from and start building the next generation of our systems. Now we're going to bring in the geosats, which we know will drive a lot of value, but we want a system that knows how to work really well with these satellite constellations and to build things where our verification metrics are already in place and we know what the end goal we want to use is. Apologies for going through that quickly, but I do want to leave time for the other speakers. Thanks very much for listening. Hope you guys saw some things that you find interesting there, and overall takeaway that the R2O cycles for Tomorrow IO are very native as we have to go to customers, but then the decisions, the skill scores that we see come back and feed these research cycles again. Thank you for your time.